Hello, class. So this is going to be the last video on this section. We're talking about general solutions of differential equations. It's going to be short because after this example, we're going to go to a new topic on classification of differential equations. We already talked about one sort of classification. We talked about type. There's either ordinary or partial differential equations. So since that's a bit of a change of topic, I'm just going to do a short video to get through this example. And then the next video, I'm going to start on the next topic. So example 11, assume that in example 9, so example 9, if you remember, is where we came up with this differential equation, right? So this was modeling the bacteria population, the growth of the bacteria population. So we already know what's the differential equation for this. So dp dt equals kp. Then we also know what this general solution is, right? Found that in example 10. General solution is p of t equals c e to the kt. Okay. So now let's see what this problem is asking. Assume that in example 9, you're also given that the initial population is 100 bacteria. So we're given an initial condition. The initial population is 100 bacteria, and after 10 days, the population grew to 17,000 bacteria. So we're given 2 extra pieces of information. We want to find P of t that satisfies these conditions. So usually, initial conditions are ones where t equals 0. Again, t equals 0 usually represents the time when you start the model. So let's first write these conditions as mathematical equations. As I mentioned, t equals 0 means the start of the model. Saying that the initial population is 100, we have a function for population. So it's basically saying that p of 0 equals 100. For the other ones, it's t is in days. So after 10 days, the population is 17,000. The same as saying that p of 17 equals 10,000. Again, p, remember, represents the population t days after or since the start. Right? So 17 days after the start means t equals 17. As I mentioned in previous videos, this is called an initial condition because it happens at the start of our model or at the start of when we're measuring things. And this here, it's not called an initial condition, but a boundary condition. The easiest way to remember this is if it's not happening at the start, it's a boundary condition. If it's happening at the start, it's an initial condition. Right, so t equals 0 is the start. T equals 17 is not the start. Okay. Now, we want to use these so that we have, because remember, this is a family of functions. This is infinitely many functions. In fact, all of the functions that satisfy this differential equation. Again, these are conditions because they limit the functions that can satisfy it. Right? So number of functions that satisfy both this and this are less. It's not all of them. Right? So how do we go about this? This is actually just the basic college algebra problem. You can just use these equations to solve for the unknowns. Right now we have 2 unknowns. Right? We have a arbitrary constant c and some proportionality constant k. So let's go ahead and use this information. Plug in p of 0. That means wherever you see a t, plug in 0. So c times e to the k times 0. That should be equal to 100. Now let's simplify. E to the 0 is just 1. It's just 1, right? Anything to the 0 power is 1. So it just becomes c equals 100. So from this initial condition, we found what our arbitrary constant has to be. So the arbitrary constant has to be 100. Now, we're going to use the other condition to solve for k. Okay, so p of 17 equals, just plug in 100 for t. 17 for t. And this should be equal to 17,000, sorry. So 17,000. And now let's just try to solve for k. So 100 e to the k times 17 equals 17,000. Divide both sides by 100. So e to the 17k equals 170. Let's just cut off 2 zeros. Take the natural log of both sides to undo the exponential. I guess, again, they're inverse functions. So 17 times k equals the natural log of 170. Finally, divide both sides by 17. And that's k. Now, that's going to be a really weird number. Let me put it in my calculator. This is something for which it could be useful to have calculators. I prefer if you leave k as it is, like an exact number, natural log of 170 divided by 17. The only problem is that doesn't give us a lot of information. I do want to get an approximation so you see about approximately what this is. This is approximately 0.302. If I have something like this, usually it's round to 3 decimal places. That's fine. So we found what k is. So what's our population function? What's 100 e to the, oh, let me make a note of this. Since this is an approximation, right, this is not the actual exact number, anytime you use approximations, you want to write this symbol here. Because again, we can't use equality because this is not equal to that. It's an approximation. Since I already stated that it's an approximation here, it's fine for me to write equality here. I already know it's an approximation. I don't need to write it again. So 100 e to the k was 0.302 times t. And that's the population function that satisfies this differential equation and satisfies both this initial condition and boundary condition. So let's say you wanted to know what would be the population after 20 days, just plug in 20 into this population function. And that's the idea. So hopefully this is a good review of how to solve things algebraically. That's basically why I do it, and also to introduce the notion of what a boundary condition is. If it's not an initial condition, it's a boundary condition, and think of it that way.